Today, I'm going to talk about thermal expansion. Thermal expansion is when a material expands as its temperature increases. Temperature is a measure of how much an object's molecules are vibrating. The higher the temperature, the greater the vibrations. Of course, these vibrations take up space. So as a molecule vibrates more, they take up more space. This is the source of the expansion, vibrating molecules pushing against each other. However, not all materials expand at the same rate. The rate of expansion is determined by several factors, but the biggest is the type of bonding between the molecules. Materials with stronger bonding types, such as the covalently bonded wood, will expand less than materials with weaker bonding types, such as the metallically bonded copper. As a rule of thumb, the better something conducts heat, the more it will expand. Interestingly, there are a few materials with negative thermal expansion, in that they expand when cooled. The most common example of this is ice, which forms hydrogen bonds as thermal energy is removed. The hydrogen bonds are the source of this negative thermal expansion, because they set the water molecules apart farther than the vibrations. However, it should be noted that negative thermal expansion is extremely rare. We can describe the amount of thermal expansion mathematically. To do this, we need to determine what factors affect thermal expansion. As mentioned previously, one factor is the change in temperature, written as delta T. I also mentioned the effect of different types of bonding. However, it is difficult to quantify bonding types. As such, a variable called the coefficient of thermal expansion is introduced to account for this and other similarly hard to quantify factors. The values of this coefficient, labeled alpha, change from material to material and are determined by experiment. Luckily, these experiments have already been done, so you can just check online for the coefficient of thermal expansion for a given material. There is one additional factor affecting the amount of expansion: the number of molecules. The more molecules we have, the more our object will expand. In the case of an approximately one-dimensional rod, we can account for this as the initial length of the rod, L0. Now, we don't actually want length, we want the number of particles, but we can convert between these two using the density of the material, and the density is just included in the coefficient of thermal expansion. If we multiply these three factors together, delta T times L0 times alpha, we find the change in length of the rod, delta L. We can easily expand this to 2 or 3 dimensions by using the initial area or volume of the object. In this case, we now get the change in area or change in volume, respectively. Since the density of material changes from 1, 2, or 3 dimensions, we have a different coefficient of thermal expansion for each number of dimensions. Thermal expansion can be both annoying and useful. In the case of infrastructure, it is more often annoying. In summer, when it gets warmer, structures, such as bridges, expand. Nothing can be done to stop physics, so if you don't account for this expansion, the bridge will buckle, possibly causing it to weaken and collapse. That is why some bridges have those zigzag spacer things. It allows the bridge room to expand in the summer. Since expansion is based on length, the longer the bridge, the more of those spacers you'll need. Some bridges that are especially short and made out of materials that don't conduct heat very well, such as a small stone bridge, don't need spacers. In these cases, the expansion is minimal enough to just be absorbed by the bridge. Of course, this isn't just with bridges. It happens with everything. Power cables sag for basically the same reason. Just as things expand when heated, they contract when cooled. So in the winter, power lines contract. And if they weren't given the extra sag room to allow for the contraction, they would break. Now, thermal expansion can also be useful. For example, it provides the basis of some heat gauges. Since different materials have different thermal coefficients, they expand at different rates. So, you can slap together a material with a high thermal coefficient, such as copper, and a material with a relatively low coefficient, such as aluminum. Then, when this thing is heated, the aluminum will expand less than the copper, causing it to bend towards the aluminum. Since copper is also a great electrical conductor, you can place this in a circuit. So, if the 2-metal heat bender gets too warm, it will bend away from the rest of the circuit, creating a gap and stopping the current flow. This can then be used to turn a heater off when it gets too warm. Nevertheless, hope you enjoyed it, hope you learned something, and see ya!